Let's go ahead and start 6.5, the natural base e and graphing exponential functions. You know about the famous numbers pi and I. Pi obviously is the most famous number you've ever seen, 3.14159265, and it goes on forever. And you also know about I. I is the square root of -1. We learned that earlier this year. There's another famous number, however, that if you take Algebra 2, you absolutely have to learn about. And I'm going to show you how that number comes about. So here we have f of n equals 1 plus 1 over n, and all of this is raised to the power of n. What we're going to do is we're going to plug in 10, 100, 1,000. You can kind of see the pattern. We're going to go ahead and this is going to be our input, and we're going to see what our outputs are. And you're going to see a pattern form from this. We'll use our calculator to do this, by the way, because by doing this, you'll see we're going to get decimals. So let's go ahead and plug 10 in for n. So what does that look like on our calculator? If I plug 10 in, so that means I'm going to have parentheses 1 plus 1 divided by 10 raised to the power of 10. So I got 2.5937, and I know we've been rounding to 2 places a lot, but we're going to round to 4 places here. This might be a little hard to squeeze in here, but 2.5937. Let's go ahead and repeat this for all the other values. So 1 plus 1 over 100 raised to the 100. We got 2.7048. Let's just keep going here. 1 plus 1 divided by 1,000 raised to the power of 1,000. We got 2.7169. Repeat. 1 plus 1 divided by 10,000 raised to the 10,000. We got 2.7181. Do you see what the pattern is doing? Do you see that it's approaching a number? It looks like it's kind of just getting closer and closer to whatever number that is. 2.7183. So what we have here is what we call it's called a limit in math. And as your n value gets bigger, and if you were to go even further, you're actually approaching a certain number. This number, kind of like how pi equals 3.14, and kind of like how I equals the square root of -1, the number that we're approaching is called e. E is, just like pi and I, a very famous number in math. Now, e, just like pi, is equal to something, so just some number. Now, I'm going to show you where you can find e on your calculator if you want to find it. So, e is... Oops, I actually forgot where e is. Well, okay, if you look right here, where the ln button is, if you see the blue above it, it says e to the x. So I'm just going to raise e to the 1, because e is really e to the 1. I could put a little 1 here, e to the power 1. So e, if you look at what we got here, e to the power 1, or just e, is equal to this decimal. And look at what we have here, and look at what we had here. Remember we were approaching this number? Do you see how it's 2.7182, like the first number matches and all the 4 digits after the decimal match? Now, these digits don't match, but that's because, remember, we're approaching e. If we were to go further along in our table, we would hit this number. So, for our purposes in our class, we're going to say that e is approximately equal to 2.71828. So you have a third number now that you know of that's famous, and it's very practical in real-world applications, as we're going to see a little bit later. But I wanted to show you where e comes from, in case you were wondering. It's not just some random decimal someone made up. There's actually a way to get that number. E behaves like any other number. Just want to show you that real quick. If you have e to the second times e to the fifth, remember, that's just a property where you add the exponents. So this is equal to e to the 7. You can leave it like that, or if I wanted it as a decimal, we can just plug it right into our calculator. Just like the button I showed you right here. This is the blue, so you have to hit second, ln, or e to the x is what it says. Hit the 7. And so e to the power of 7 is approximately 1096.63. That means if you took e and multiplied by itself 7 times, you would get this number. Even this right here, e to the 5th over e to the 8. Remember, you subtract exponents in this way, so you get e to the negative 3. You can leave it like that. You can even write it as 1 over e to the 3, because that's our negative exponent property. You can even just plug into your calculator if you want to get the decimal equivalent. You hit second e. You can do negative 3 like that. You can even do 1 divided by second e to the 3. And either way is fine. So I typed in this and this, but we got the same thing. Rounded to 4 places will be 0.05. Like I said, E is used in many real-world applications. Let's go ahead and see one of those applications now. You're going to want to copy this down. This will be on the test that we have for this unit. Okay, so you copy this down. We learned about increasing and decreasing rates earlier in this chapter, and even with interest problems. But in math, there's also something called compound interest. The difference between the interest we learned before, the interest rate problems, and compound interest is with compound interest, you're making money off the money you've already made off the money. So, kind of weird, but basically, when you make money off the money you invested, the interest gets compounded so that you make money off the interest you made. So it's like a snowball effect. You're making money off the interest you've already made. So if you can get compound interest on an account, that's the one you want to go for, because your money just starts snowballing, and that's what happens. So now, interest is compounded in intervals of time. For example, daily, weekly, monthly, quarterly, annually, biannually, meaning that if it's daily, more money is put into your account every day. If it's weekly, more money is put into your account every week. Monthly, every month. Quarterly means 4 times a year, so every 3 months. Annually means every year. Biannually means 2 times a year. Anyways, if your interest is compounded in the interval of time, you got to use this formula. I told you what all the letters mean. A is your final amount. That A is over here. P is your initial amount, whatever money you're investing. R is your rate. Remember, we have to, because your rate's probably going to be given as percent, you have to convert it by moving the decimal over twice or divided by 100. N is the number of times compounded in a year. So like I said, for example, if you're compounding daily, how many days are in a year? There's 365. So if you're compounding daily, your end value is 365. If you're compounding weekly, how many weeks are in a year? 52. Oh, by the way, you might be saying, oh, what about leap year? And actually, this year's leap year. For our purposes, let's stick with daily. It's 365, not 366. If it's monthly, there's 12 months in a year, so your end value would be 12. If it's quarterly, that means 4 times a year. If it's annually, that means 1 time, and biannually means 2. There's other things you could do, but we're just going to stick with these in my class. And then T is the number of years. So don't confuse N and T. N is the number of times you get compounded in a year, and T is the actual number of years. So this is the formula we'll use for compound interest if it's compounded like in every day or every week or so on. There's also a way to compound interest continuously, meaning that it never stops compounding. Every nanosecond, your interest is compounding. It's like a continual flow of money into your account. And this is where E pops in. E is all about compounding continuously. And the formula, which is nice, is pretty simple. It's A equals P, E to the power of RT. And maybe some people like to put parentheses around the exponent RT. This is not times RT. This is E is to the power of RT. Okay? Again, E is about 2.71828. Again, P is still your initial amount, A is still your final, R is still your rate, and T is your time. You don't need N for this because, well, we don't need number of times compounded in a year because it's continuous. Okay, so you deposit, so we're going to go ahead and do this problem. You deposit $4,000 in an account that pays 6% interest. What is the balance after 4 years if the interest is compounded daily, I forgot question marks, monthly, quarterly, annually, and continuously? All right, so we're going to do all 5 of these. We're going to be using our calculators for this. So let's go ahead and just identify a few things. P is 4,000 because P is our initial amount. Our interest rate is 6%, but here's the decimal. We're going to have to move it over twice. So really, our R is 0.06. So we have our P, we have our R. No, so it says 4 years. So T equals 4 because that's the number of years. And then we need N. N is going to be different depending on how often you're compounding. So, for example, if we're compounding daily, N represents the number of times you're compounding in a year. So how many days are in a year? We said we're going to stick with 365. I don't know why I put 365 in parentheses. Don't judge me. So N equals 365 for part A. Let's go ahead and just identify what are our N values. So for daily, it's 365. For monthly, how many months are in a year? So N is going to be equal to 12. Quarterly, so you divide a year into 4 parts. So N equals 4. Annually, you say N equals 1. And continuously, well, like I said before, continuously means that we're not using N. We're going to use this formula instead. And some people, by the way, call it the PERT formula. You can probably see why. So we're not going to be using N. In fact, we're going to be using the other formula. So just to remind you, for parts A through D, we're going to use this formula. For part E, we're going to use what we call the PERT formula for the compounding continuously. So now that we have everything we need, we got P, we got R, we got T, we got our different N values for parts A through D. Let's go ahead and just plug into the calculator. It's pretty easy. I'm not going to set up every formula here, but I'm going to show you how you would set up part A. So remember, the formula is A equals P times 1 plus R over N to the NT. So what do we know? We know that P is 4,000, so I make that replacement. Inside the parentheses, I have 1 plus R over N. So R is 0.06 divided by N, which is 365. Close. And then I have N times T in my exponent. Again, N is 365 and T is 4. So I have 365 times 4 in the exponent. All right, let's go ahead and we can plug this right in all in one shot. We have 4,000. 1 plus 0.06 divided by 365. And your calculator will take care of order of operations for you if you type it in just the way it looks here. And then raised to the power of 365 times 4. Now, you can either figure out what 365 times 4 is ahead of time and put that number as your exponent, or if you're going to just do 365 times 4, you need to put parentheses, because with exponents, your calculator would only do power 365. And then it would multiply the end result by 4. You don't want that to happen. So you need to, if you're going to keep it like this, and that's fine, just make sure you put your exponent in parentheses. And by the way, I put the caret there, obviously, because, that's our exponent button. All right, let's see what we get. So we put $4,000 in, and if we leave it in there for 4 years at that interest rate, compounded that much, you get $5,884, and it's going to round up to 90 cents. All right, let's go ahead and just do this again. I'm going to show you a trick here. You don't have to do this trick. You can go ahead and type everything again if you want to, but if you hit second and the enter button, that's really going to hit entry. And if you do that, look what happens. it pops up with the same thing you typed in the last problem. Why do you want to do that? Well, basically, when we do part B, everything's the same except what changes is n. And if you just want to change n, you can now just go back and type in n equals 12, where originally it was 365. We might have to use the delete button to change 365 to 12, but that's not hard. So I hit the delete button, I overwrite the 365 with the 12. There is another 365, so I'm going to hit the delete button again and put a 12 here. And this way I don't have to sit there and waste my time retyping every little thing, because I'm only changing n. Everything else is still 4,000, it's still that interest rate, it's still the number of years 4. So now, for part B, I got $5,000, $5,081.96. Not much of a difference between daily and monthly. All right, let's do quarterly. Again, if we do second entry and just change the 12 to now a 4, we're going to have to hit the delete button. Just make sure the 12 becomes 4. And again, you don't have to do my way. You can just retype everything if you want. All right, for quarterly, if you leave it in so it only compounds 4 times a year, you get this much money. Okay. All right, let's go ahead and do it annually. So we're going to replace our 4s with 1s. Hit second entry. Now I can go back and edit it. And for annually, we get $5,049.91. We're gonna pause here for a moment. Well, you don't have to pause the video. That's not what I mean. But look at what's going on. As n decreases, you're making less money. So the more times it's compounded, the more money you're making. Now think about continuous. If it's continuously being compounded, it's like over and over and over as time goes on, it's just continually compounding. We should make more money, right? So that's our prediction. As we continuously compound our money, we should make more than any of these because it's been happening more, a lot more. Our highest value is this, so we should expect to go even larger than this when we do this. Now, we're not using the same formula though, so I don't need to keep this in here in the calculator anymore. We're using the other formula, the A equals PERT formula. So that means P is 4,000. We're going to use E and then raise to the RT, which is 0.06 times 4. Okay? Because PERT. And you can plug this all in one shot as well. You have 4,000. Hit second ln. And then, so you have 4,000 e to the power of, and then 0.06 times 4. So we get 5,084 point. Actually, that would just pretty much be 5,085, wouldn't it? In 0 cents, we'll say. Not much of a difference, but if you were to put more money into the account or have a better interest rate, or more time, you would see more growth. You would see a bigger divide between these two. It'd be more separate. Okay. With base E, you also have what's called natural logarithms. If you have log base E of x, it is called a natural logarithm. This actually has special notation, and we need to get used to this. So if you have base E, remember E is that number we've been talking about. E is 2.71828. You actually can write it as ln x. Now when you write it like this, the base E is still there. You don't need to write it all the time, but it's still there. So this is right, and the way you say it in words is without the either. It's the natural log of x. Okay, the natural log of x. Okay, so we have ln x. So you probably noticed that we have the ln button. So I kind of lied when I said there's only one log button on your calculator. You actually have two. So right below the log button that we've been using a lot is the ln button. And so if you just do ln 5, get 1.61. It's easy, right? ln 6, 1.79. Now, we can do this one without using a calculator. What did I just say about natural logs? What's the base of this? The base is what? The base is e. Don't let the ln throw you off. This is still read as log base e of e. What happens when the base and this number match? It's equal to what? The exponent. And what's the exponent on e? If there's no exponent written, it's 1. So if this and this match, what is this whole thing equal to? 1. So basically, a quick trick is just to say ln of e equals 1. That's a quick rule of thumb there. Might need to know that. Hint, hint. Okay. Last thing I need to show you, and sorry this video is a little longer, but you can deal with it. And this will be on the test, is graphing exponential functions. We're going to graph f of x equals 3 to the power of x. Then we're going to graph g of x equals 3 to the power of x minus 4. We're going to state the domain range for each. So what I'll do is set up an xy table. We're going to do f of x first. We don't need to make this super complicated. What I would do if I were you is make the table, and you're going to put -2, -1, 0, 1, and actually let's go ahead, I'll go all the way up to 2. We're going to go ahead and plug all this stuff in. So we're doing this for f of x. So if I plug -2 in right here, I have 3 to the -2, which is 0.11. If I plug -1 in, 3 to the -1, it's 0.33. If I plug 0 in, let's think about this. Let's use our brains. 3 to the power of 0. Well, anything to the power of 0 is 1. In fact, we don't need a calculator for the rest of this. Watch. Plug 1 in. What's 3 to the power of 1? It's 3. Plug 2 in. What's 3 to the power of 2? That's 3 times 3. That's 9. So you can use a calculator for negative ones, but for the positive ones, it should be pretty easy. Remember, anything to the power of 0 is 1. So now I have -2.11. Let's find that point. -2.11. So it's very, very far down there. It's right there. -1.33. -1.33 is right here. 0, 1 is right on the y-axis right there. 1, 3 is about right here. 2, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 9 is way up here. And the way you connect it, this actually has an asymptote. Remember asymptotes? That's that dotted line. The asymptote is the x-axis. So your curve, it starts off really small right here, very close to the asymptote. Remember, it gets infinitely close, but doesn't touch. And that's the shape of your graph. So it starts off small, and then it explodes. It goes up. And this is why they call it an exponential function. You'll hear this in the real world, by the way. They'll say something has exponential growth, meaning that it starts off small, but it grows rapidly. So anytime you hear exponential growth in the real world, they're talking about rapid growth. All right, so that's that function. And when you look at g of x, we have 3 to the power of x minus 4. Well, that's this function. It's just with a minus 4 at the end of it, right? They both have 3 to the power of x, but there's a minus 4. What that means is this function g of x is just this function shifted down 4. I'm going to switch to a different color here. So to graph g of x, I just take every point I just drew and shift it down 4. Which means that also shifts down my what? My asymptote. Remember how I said my asymptote was on the x-axis? Well, I'm going to have to shift it down 4 so that my asymptote now is right here. So that's what the minus 4 after the 3 to the power of x, that's what it does. It shifts down your asymptote. Alright, so let's go ahead and shift every point that we drew down. So it's -2, it was -2.11. It's still -2, but now we're down to about right here. We had -1.33, so it's about right here. I had 0, 1. That's going to put me at 0, -3 right here. Sorry, I'm going to be a little off here. Human, and these markers are huge. 1, 3. If I move it down 4, it's still 1, but now I'm at -1. And 2, 9. I'm still over 2, but 9 minus 4 is going to put me at 2, 5, like that. And it still has the same shape. It gets infinitely close to the asymptote, but never touches. And then it just shoots right up. One last thing we have to talk about is domain and range. Domain, we'll call D. Range, we'll call R. Do that for both of these. The domain, all your x values, well, this graph goes to the left and to the right forever. Even though this shoots up, it's also going this way forever. So your domain and range, your domain is all real numbers. So for any exponential, that's going to be true. So I'm going to even say that over here. The domain of any exponential is all real numbers. The range, however, is not all real numbers. The range is going to depend on the function. So this graph right here, it doesn't really have a bottom point, but it gets closer and closer to the asymptote. So we're going to say our range starts at 0, because that's where our asymptote is on the y-axis. So now, remember, there's no actual point at 0, so we're going to say our range is y is just strictly greater than 0. Now, is that the case over here? Well, look at where our asymptote is. It's at -4. So we're going to say our range is y is greater than -4, because that's where our asymptote is, because of the shift down that we had on this function. Okay, so you'll get plenty of practice on this next class. I was told to give some shout-outs, so here we go. Shouting out period 1, period 2, period 3, period 4, period 5, period 6, and period 7. Yes, you all wanted me to shout you out. So there you go. And a couple specific shout-outs. Got Lady Kobe, period 7. What's up? Aaron Hernandez, not the former Patriots player. BC Youngfly and D-Money. Special shout-out to you guys. And go check out the Dr. 5657, his YouTube channel. And I had a joke for you. Okay, here's the joke. Here we go. This is great. What do organic mathematicians throw into their fireplaces? Natural logs.